Thank you, Jacob. My name is Mitropoulos-Rundus, and alongside me today is the PI of this study, Schwarz. In a vehicle powered by internal combustion, there is a significant energy loss when the driver presses the brake pedal. When the brake pads pinch the rotors, friction is created and used to slow the vehicle. This friction turns the kinetic energy into heat, which is then lost and cannot be used by the vehicle. This is the traditional form of braking known as service braking. Regenerative braking is a system that does not use the service brakes of the vehicle. It is typically used in electric vehicles to recapture the kinetic energy that would normally be lost while braking using the service brakes. Electric vehicles don't have a transmission and instead use a combination of regenerative braking and service braking. When the driver releases the accelerator pedal, the vehicle immediately begins to slow down. Regenerative braking works by putting the motor in reverse mode and running the motor as a generator, allowing braking torque to slow the vehicle while generating electricity. Regenerative braking has the potential to save from 8% to as much as 25% of the total energy use of the vehicle. Regenerative braking can be triggered via accelerator pedal release or brake press. Some examples of where regenerative braking is currently being used are in Teslas, the Toyota Prius, and the Nissan Leaf. Currently, there is little research on the human factors and safety implications of regenerative braking. Research looks at making regenerative braking more efficient and effective, but does not investigate the safety implications. A central question not yet examined in the literature is whether regenerative braking provides a negative acceleration advantage in time and distance over traditional service braking. Since there is no standard intensity of regenerative braking, different levels must be explored. Theoretically, regenerative braking should provide a braking advantage over service braking because the braking process begins as soon as the driver releases the accelerator pedal rather than when the driver presses the brake. This research explores this difference to determine any advantages that regenerative braking may have over service braking.
Thanks, Christopher. I'm going to talk a little bit about the Tesla that we used to collect some data for this study. We have several research vehicles, one of which is a Tesla Model S, that's a typo, 75D. And with that vehicle, we instrumented it with several different types of hardware. One was a Mobileye front camera, which used to be what Tesla used, and then they moved away. So we put on our own Mobileye and use it for data collection. And as well, there's some Ergoneers instrumentation on there. And then finally, for a couple of variables that the others didn't capture, we have a VBox data logger. And so basically we took the Tesla out on the road and collected some data with it in both there's two modes of regeneration on the Tesla. There's a higher level of regenerative braking and a lower level. And this is one example that you're seeing here, one level. And for data from a whole drive, and when you look at the phase plane, plotting acceleration versus speed, you get all these loops for all the different times that you accelerate during a drive and all the different times that you brake during a drive. And in showing this data, I've already filtered out all the times when the person used the brake pedal. So we're only looking at those times when the vehicle is using regenerative braking. Now, in a normal car with service braking, this would be called coasting, and the levels of deceleration that you're seeing in the red would be quite a bit smaller. But with the Tesla, with regenerative braking, you're seeing quite a bit more deceleration. So to get at this, I went into this data and tried to find all of the local time histories of each braking period, and in the top graphs are those periods of time where the driver's foot was off the pedals, the Tesla was in regenerative braking, and the vehicle was slowing down. And you can see And it's pretty linear, except towards the end when it sort of tapers off and the deceleration becomes less. On the left is the low level of deceleration or of regen braking, and on the right is the higher level of regen braking. So if you go through each of those lines and calculate the slope, as I said, it's fairly linear, and you could easily estimate the slope from each of those and plot those on a graph. That's the bottom. And so the red ones are the high level of regen. The teal or bluish ones are the low level of regen. And then you can see in the lines on top that the speed doesn't always go to 0. Similarly, the person's foot may not even come all the way off the throttle pedal, the gas pedal. The regen braking will actually kick in as the person's foot releases pressure, but they may still be depressing it a little bit. So I was trying to understand all the nuances of the speeds during which this thing is braking, the position of the foot on the throttle pedal, whether they were just lifting off or partially or completely, and then the modes of the regen. And so you could develop a very complicated model based on all that, but I was trying to get at what the simplest possible characterization of regenerative braking was. And so from all the dots on there, we basically took some averages to sort of get the average level of regenerative braking. And so for the low level, a lot of those are up at 0.5 G, negative 0.5 G, and in the higher level, it can go all the way up to negative 2 G, not G's, meters per second. Sorry, G's would be quite strong. So we collected all this data from the Tesla and came up with a simple model of regenerative braking, and then implemented that in the simulator. And now Christopher is going to take it from there and talk about the experiment that we designed.
Thank you. The National Advanced Driving Simulator, NADS-1, was used for this study. The NADS-1 utilizes an actual vehicle cab and projects scenery 360 degrees around the driver on the interior walls of the dome that houses the cab. The vehicle cab is mounted on 4 independent actuators that provide vibration associated with driving on varying road surfaces. The entire dome is mounted on a motion base that can independently provide surge, sway, heave, roll, pitch, and yaw cues to the driver. The NADS-1 has a 13 degree of freedom large excursion motion base that can move around a space with a dimension of 20 by 20 meters and generate accelerations up to 0.6 G. The surface braking vehicle dynamics were based on the Oldsmobile Intrigue, while regenerative braking, as Chris said, was modeled from the data collected from the NADS Tesla Model S75D research vehicle. The NADS-1 features a full 2014 Toyota Camry cab inside the dome. It has a programmable center console screen that can display what is needed for the research study. The picture on the bottom shows what was displayed on the screen. This will be explained later on in the presentation. For this study, 30 participants between the ages of 21 and 45 years, split by gender, drove in the NADS-1 driving simulator. All were required to have an active driver's license. Participants were recruited through the NADS volunteer database, which contains over 5,000 individuals. The study followed a between subjects design, which meant there were 10 people per condition. The study compared 3 braking conditions: service braking, the low level of Tesla regenerative braking, and the high level of Tesla regenerative braking. The low level of regenerative braking slowed the car at approximately 0.02 to 0.05 G, while the high level slowed the vehicle at approximately 0.15 to 0.2 G. The low level regenerative braking felt similar to a coast when the accelerator was released, while the high level of regenerative braking slowed the vehicle at a much more noticeable rate. Participants were randomly assigned to one of the 3 experimental groups. For the entire length of the drive, the participant was instructed to drive as close to 55 miles per hour as possible. Throughout the drive, there was a lead vehicle in front of the participant vehicle that had a fixed gap. The environment was a rural 2-lane highway. It took place during the day with light traffic. The study had 3 separate braking events, 2 mild and 1 severe. These will be expanded upon later. During the drive, the participants had 2 tasks they were instructed to engage in. The first was a number recall task. This appeared on the monitor on the dashboard of the vehicle. This distraction was used for both mild events to prevent the driver from picking up cues that a braking event may occur, but it was not used for the severe event because there were no visual cues that a braking event was about to occur. The number recall task also occurred throughout the drive, so the participants stayed engaged and could not use the task to predict an event. The task occurred at a rate of about once per minute. The driver was notified of the number recall task via a chime. About a second after the chime, 5 random, single-digit numbers were presented one at a time on the center console, approximately a half-second apart. After all 5 numbers were presented, the participants had to recall all of the numbers out loud in the correct order. The second task the participants engaged in was the speed task. As I said earlier, drivers were instructed to drive 55 miles per hour. In order to assist them with the task, the dial to the right was placed on the center console screen. If the needle was in the green zone, the driver's speed was acceptable. If the needle was too far to the right, their speed was too fast. If the needle was too far to the left, their speed was too slow. The simulated drive began with the participant vehicle at a standstill. In front of the participant vehicle were 2 lead vehicles, both with a fixed headway gap. The 2 lead vehicles immediately began driving at a set speed until the driver exceeded 20 miles per hour, at which time the lead vehicles changed to a maintain gap behavior. The participant had to accelerate to 55 miles per hour and remain at this speed throughout the drive. The time between the start and the first event gave the participant more than enough time to get up to speed without the lead vehicles getting too far ahead. The first event began with a number recall task for the participant to complete. During this task, the vehicle in front of the vehicle lead vehicle turned right onto another road, causing the lead vehicle to slow down. This is the first mild event. Following the event, there was just 1 lead vehicle in front of the participant vehicle, and it remained there for the rest of the drive. After each event, the participant was expected to accelerate back up to 55 miles per hour. The second event began with a number recall task for the participant to complete. During this task, the lead vehicle braked because of a deer on the side of the road. This was the second and final mild braking event.
7367.
The final braking event did not have a number recall task. The computer-simulated vehicle slowed rapidly for no apparent reason until it came to a complete stop.
This is the end of your drive. Please shoot.
This was the final and most severe event. Once the participant vehicle came to a complete stop, the drive was over. This study used many measures to explore all possible advantages and disadvantages that regenerative braking might have when compared to service braking. The first measure was crash or no crash. Another measure was time to collision. Time to collision looks at how much time the participant vehicle has at a certain moment before it collides with the vehicle in front of it. This was measured 3 ways: time to collision at throttle release, time to collision at the first brake press, and minimum time to collision. The third measure was the time it took to begin the braking process. The figure on the right shows the timeline of the braking process. When time equals t0, the lead vehicle's brake lights come on. When time equals 1, the participant releases the accelerator, and at time 2, the participant presses the brake pedal. The time to begin the braking process was measured using 3 equations: from time 0 to time 1, from time 0 to time 2, and time 1 to time 2. The fourth measure was distance traveled during the braking event. This is measured from the moment the lead vehicle's brake lights come on until the participant vehicle begins to increase speed after slowing down, or in the case of the last event, comes to a complete stop. The fifth measure was maximum brake pedal force. This was measured in pound-force. The sixth measure was brake time. This was measured 3 ways. The first was from the time of the initial brake press, time 2, to the time the driver takes their foot off of the brake pedal, time 3. The second is from the time of the accelerator release, time 1, to the time of the brake release, time 3. The third is the total brake time, which is measured from the time of the lead vehicle brake lights turning on, time 0, to the time the driver releases the brake pedal, time 3. The seventh measure looked at the negative acceleration of the vehicle. This measure explored average negative acceleration during the entire brake time and the average acceleration of the vehicle from the time the driver removes their foot from the accelerator, T1, to the time the driver presses the brake, T2. Data reduction of simulator data was done using MATLAB, and data analysis was done through SPSS. The Kruskal-Wallis test was used to compare means between the levels of regenerative braking because the residuals were not normally distributed, and a non-parametric test was needed to determine whether there were statistically significant differences among the 3 groups. The confidence interval used to determine significance was 95% for all tests. Columns 3, 4, and 5 of the table show the output for all significant values from the Kruskal-Wallis test for events 1, 2, and 3. For this analysis, all 3 events were tested separately, and within each event, the 3 levels of braking were compared. For all 3 events, the only measure with asymptotic significance was average acceleration of the vehicle and the time interval between accelerator release and brake press. The last column in the table shows the output for the Kruskal-Wallis test when the first 2 events were combined as one event. In order to combine the 2 events, the average value for each variable in the 2 events was taken. The 2 variables with significance were average acceleration of the vehicle and the time interval between accelerator release and brake press, and maximum brake force. Here are the box plots for the significant measures. As you can see, the high level of regenerative braking is the mean that is statistically significantly different, and there are non-significant differences between service braking and regenerative braking low. Since the braking process begins earlier with regenerative braking than service braking, regenerative braking should provide a negative acceleration advantage in time and distance over service braking. The significant measure, which compared the 3 means of the average acceleration of the vehicle and the time interval between throttle release and brake press, did indicate that an acceleration advantage was imparted to the driver. However, this advantage was not observed to propagate into traditional safety measures such as minimum time to collision. When events 1 and 2 were combined and maximum brake force showed a significant difference in means between one of the 3 conditions, this gave insight into how regenerative braking was being used. While maximum brake force showed a statistically significant difference, measures such as average acceleration and time to collision were found to not be statistically significantly different. The participants were able to properly gauge the assistance that regenerative braking was providing, and therefore did not have to press on the brake pedal as hard because regenerative braking was giving them an advantage in the braking process. With just a 5-minute warm-up, participants were able to adjust how they typically braked and incorporate regenerative braking into their braking strategies. This also gives insight into what people use in their perception in order to brake. People rely more on visual cues, such as looming cues and time to collision, than on pedal force. In order to explore whether regenerative braking provides a negative acceleration advantage more in depth, future study designs should entail more severe braking events. These events should be severe enough to the point where the driver is at a high risk of colliding with the lead vehicle, forcing the participant to brake more aggressively. Also, to explore the decomposition of driver response in electric vehicles with regenerative braking, and to explore the possibility of implementing dynamic regenerative braking. Dynamic regenerative braking could alter how quickly regenerative braking slows the vehicle, depending on the environment around the vehicle. Regenerative braking would likely change in situations that require quick braking, but not automatic emergency braking. I would like to thank the following people for all of their assistance and support throughout the project, specifically Chris Schwarz, the PI of the study, Daniel McGeehee, my advisor, and Rose Schmidt. I would also like to thank Safer-Sim for funding this project. All right, and we have time for some questions.
Thank you, Christopher and Chris. We will open up the chat box for anyone. If they have questions, you can feel free to type them in there. So we do have a question that came in. Where do you plan to go next with this research?
So the next step is to possibly explore regenerative braking a little bit more by creating a study with more severe events. Even the severe event in this study was not quite as severe enough to the point where we had any collisions. So the next step would be to put the driver in some scenarios where they are at a high risk of colliding with the lead vehicle, and they really have to press on the brake pedal and react quicker. We're also looking into exploring dynamic regenerative braking, so that the rate at which regenerative braking slows the vehicle changes depending on the environment around it. So for example, if someone is driving down the road and they have to stop suddenly, but it is not severe enough for automatic emergency braking, perhaps a system that implements dynamic regenerative braking could increase the regenerative braking power to assist the driver.
Great, thank you.
Thank you.
I know you showed a few examples of the vehicles that currently use regenerative braking. Do any of those have the dynamic regenerative braking that you're talking about, or is this something that will be more down the line?
So as far as we know, dynamic regenerative braking does not exist yet, so this would be something that would be implemented down the line.